Hi everyone, welcome back again. Let's look at how we can use the increments formula, the small change formula, to be able to approximate some values on the function. Let's have a look at how it works. So the small change formula, I still always think of it as that. What is that really? If I get any curve anywhere and I get 2 points very close together, where there's a small change in y, I'm writing it small, over a small change in x, it's going to be very, very close to the derivative, which is what? The gradient of the tangent to the curve at that point. So on this question here, we are talking about the point f6, and the small change to x is how far is 0.6 above, 6.02 above 6, and we've got 0.02. So let's go back to our formula and what's going on. In the formula, a small change in y approximate equals the gradient times y small change in x. So first of all, we need the gradient. So let's go back over to here and get the gradient. I've written the square root of x as a power of a half. If I differentiate it, now I'm writing the derivative instead of dividing x, I'm writing it as f dash x. So the half comes to the front. We've got an x minus 5, and we decrease the power by 1, so that's a minus a half. So that's decreased by 1. So you multiply the power and decrease the power by 1, and we would normally multiply by the derivative of the inside. But in this case, the derivative of the inside is 1. There's a 1 there, the derivative of 1x is 1. So it actually makes no difference to the question. The derivative is, we've now got the square root on the bottom with a 2 as well. So on the bottom, there's the 1 on the top, there's the 2 on the bottom. I've got a square root on the denominator of x minus 5. That's my derivative. Let's go over to here then. The small change in y is the derivative, 1 on 2 square root of x minus 5 by the small change in x. In this case, the small change in x was 0.02, because 6.02 is a little bit above 6. Now in this case, on the x, I could have also said that x equals 6. I could have a small change is 1 on 2 with the square root of 6 minus 5. You can see how easily this could go into a non-calculator section if you get nice numbers. And the small change is, in this case, 1 over 2, it's the square root of 1, which is 1, times by 0.02. So what have we actually got? This calculation becomes a half by 0.02, and the half by 0.02 is 0.01. So our small change in y is that. What are we looking for? We want the function for 6.02. So the function for 6.02 is the function of 6 plus the small change in y. So I've got the function at 6 is, let's have a look at what it is. It's the square root of 6 minus 5 plus the small change in y, which is 0.01. So what have I got all together? Square root of 1 is 1. 1 plus that is 1.01. So the approximate value for the function at 6.02 is 1.01. Could probably do it fairly close from common sense. So what happens to the same question though, if this time we're not looking for the small change of 0.02, we're looking for a small change this time of, this question becomes, it's 0.02 below 6. So it's minus 0.02. So if you go to the same formula, same question, the small change is the derivative, approximately the derivative. So you make delta y the subject, you get the derivative just like before, but this time instead of timesing by 0.02, we're timesing by minus 0.02. So that we carry that calculation all the way through, and we've got minus 0.01. So in this case, instead of getting the function of 6.02, we've got the function of 5.98. And what have we got? Function is 6 plus that. Let's have a look what it is. So instead of adding it this time, we are minusing it. So we've got the negative of 0.01, in other words, just below what we had before. So we've got 1 minus 0.01, and we've got 0.99. So there we have, using a increment formula, small change formula, to approximate values in a function with a small amount of change. Thanks.